Light can vanish in a blink. Why does energy disappear so fast? It doesn't just fade, it turns into heat, scatters sideways, or gets trapped in vibrations. Every wave you see is already on a path to becoming invisible or warm. Attenuation is the loss of a wave's forward power as it travels through matter. It happens in two ways: absorption and scattering. Absorption turns wave energy into internal motion. Electrons jump, atoms vibrate, heat rises. Scattering redirects energy sideways. Photons bounce off particles or sound waves bend around obstacles. Both processes reduce the intensity that reaches a detector. In solids, lattice vibrations absorb acoustic energy. In liquids, molecules absorb light and convert it to heat. The result is an exponential drop in signal with distance. Pause 0.8. When a wave encounters an obstacle, part of its energy is redirected. This redirection is called scattering, and it occurs at the surface of particles. Imagine photons hitting a tiny sphere. They bounce in many directions. Each scattered photon carries away a fraction of the original forward momentum. Because energy leaves the main beam, the transmitted intensity drops behind the obstacle. The amount of loss depends on particle size relative to wavelength and refractive index contrast. Larger particles scatter more strongly, creating a pronounced shadow region downstream. In acoustic waves, sound particles behave similarly, deflecting energy around obstacles. The cumulative effect of many scatterers is an exponential attenuation of the beam. Thus, scattering is a fundamental mechanism that reduces signal strength in communication systems. Pause 0.8. The crystal lattice is a periodic array of atoms bound by interatomic forces. When a mechanical or electromagnetic wave strikes the solid, it perturbs this orderly arrangement. The disturbance propagates as collective oscillations known as phonons. Each atom in the lattice vibrates around its equilibrium position due to the incoming energy. These vibrations are not perfectly elastic. Some kinetic energy is dissipated internally. Internal friction between neighboring atoms converts a fraction of the wave's energy into random motion. This random motion manifests as an increase in thermal energy within the material. The process is called vibrational or phononic absorption, because it relies on lattice vibrations. Electromagnetic waves, such as infrared radiation, can also excite these phonons directly. As the phonon population grows, the solid's temperature rises until equilibrium is reached. Thus, mechanical or electromagnetic energy is ultimately transformed into heat through atomic motion. Understanding this mechanism helps engineers design materials with tailored thermal properties. Pause 0.8. A photon arrives at an atom and carries a specific amount of energy. If that energy matches the gap between two electronic states, absorption occurs. The electron jumps from the lower to the higher level, leaving a vacancy below. This transition removes one photon from the beam, creating a dark line in the spectrum. The position of each dark line corresponds exactly to the energy difference of that pair of levels. In a plot, these lines appear as sharp absorption peaks against a continuous background. The intensity of a peak reflects how many electrons can make the transition and how strongly they interact with light. By measuring all such peaks, we map out the discrete energy ladder of the atom or molecule. This mapping is the basis for identifying substances in spectroscopy laboratories worldwide. Thus, photons act as probes that reveal the hidden structure of matter through absorption. Pause 0.8. The absorbed electromagnetic energy first becomes vibrational motion within the material's lattice. This microscopic agitation is called thermal dissipation. As atoms jostle, kinetic energy increases and temperature rises locally. Heat then spreads through conduction to neighboring regions of the slab. The rate of this spread depends on the material's thermal conductivity. In metals, electrons carry heat rapidly, while in dielectrics phonons dominate. The resulting temperature gradient drives a heat flux outward from the illuminated surface. Over time, the entire slab approaches an equilibrium temperature determined by energy input and losses. This process is governed by Fourier's law of heat conduction. Understanding this link explains why some materials feel hot after light exposure. The magnitude of the temperature rise is proportional to the absorbed power density and inversely related to the slab's heat capacity. Engineers use this relationship to design materials that either dissipate heat quickly or retain warmth efficiently. Pause 0.8's attenuation reduces the energy that travels through tissue. In ultrasound, scattering redirects sound waves in many directions. Absorption converts acoustic energy into heat within cells. Both mechanisms lower the signal that reaches the transducer. Optical imaging faces similar losses due to photon scattering. Light absorption by hemoglobin and melanin also diminishes intensity. Typical ultrasound attenuation coefficients range from 0.3 to 1 dB/cm/MHz. For visible light, tissue absorption can reach several hundred millimeters per centimeter. The combined effect is a depth-dependent exponential decay of signal strength. Understanding these parameters guides the choice of frequency and wavelength. Higher frequencies provide better resolution but suffer greater attenuation. Lower frequencies penetrate deeper yet produce coarser images. Pause 0.8's attenuation reduces wave intensity through scattering and absorption. Absorption converts energy into heat via lattice vibrations or electronic excitations. These mechanisms govern visibility, material transparency, and imaging performance.